So the logarithm of a complex number has infinitely many values. It's our first example of what we might call a multi-valued function. So how do we take the logarithm of a complex number? Well, basically we write the complex number z in polar form. So it's r times e to the I theta. But we remember that theta can be, for example, pi by 2, or it could be pi by 2 plus 2 pi, and we get the same, essentially the same angle. It's the same complex number, but we just change in the angle. Or we can have plus 2 pi n, and we basically get the same complex number, but when we take the log, then we actually get different values. So if we take the log of product, then it's the log of r plus log of e to the I something. Log of e to the I something is just the something, so the something comes down, and then we see we have all these values. So n is any integer. So like with the argument, so remember this is simply the argument, which we've said has lots of values. Theta p is the principal value of the argument. We talk about the principal value of log z, which is often denoted by a capital ln. The principal value of log z is then defined and is a single value function. It's simply the ordinary log of r plus I times the principal value. So it's therefore the value of log z when you set n equals 0 in this formula. So now you can find logs of negative numbers, which before you thought was impossible. Well, the log of a negative number is actually just a complex number. So for example, log of minus 2. Well, minus 2 is 2 times e to the I pi plus any multiple of 2 pi. So that gives us log 2 plus, and that's, 2n plus 1 times pi I. Okay, so logs of negative numbers do exist, they're just complex numbers. But there's lots of different possible values. Just like with inverse sine, for example, there's lots of different values of inverse sine. It's not so surprising. Now, when dealing with multi-valued functions, you need to be careful about identities. So identities are basically formulae which are always true. Now, certain formulae which are always true for real numbers might not necessarily be true for complex numbers, and we'll see a few examples. So that's just something to watch out for. So we define that two expressions, a and b, which involve multi-valued functions such as log, are only equal to one another if the set of all possible values of a is the same as the set of all possible values of b. Now, for an example of an identity which is obviously true for real numbers and is also true for complex numbers, e to the log z is always equal to z. You can see this simply by substituting the expression we have for log z, this thing, into the left-hand side, and what we get. So we've got e to the log z, and then log z we've just said is log r plus I, principal value of the argument, plus 2 pi n. So e to the log r, that's no problem, that's just r. And then e to the I theta p plus 2 pi n. Well, the e to the I 2 pi n we can ignore. That's just 1 always, so it's just e to the I theta p, and that's just z written in polar form. However, since log is multi-valued, log of e to the z you would normally think is equal to z, but actually it's not, as we can see. So if you take log of e to the z, what do we get? Well, log of e to the z we can write as, well, z is x plus iy, so it's log of the modulus of e to the x plus iy. Okay, so we're writing this in polar form. Okay, so it's r, we want the modulus of e to the z, which is the modulus of e to the x plus iy, plus I times the argument of e to the x plus iy, which, remember, is multi-valued. Okay, so if we take, what's the modulus of this? Well, the modulus of this, we can split it into two parts. It's the modulus of e to the x times the modulus of e to the iy. Now, the modulus of e to the iy is 1, so we're just left with the modulus of e to the x. So that's a real number. So the modulus of e to the x is actually just e to the x. It's a positive number. So now we've got log of e to the x, which is indeed x. But when we come on to the argument of e to the x plus iy, well, here we can ignore the e to the x because that's a real number. So just remember, e to the x plus iy is just e to the x times e to the iy. The e to the x bit is a real number, so we can ignore that, and we just get the argument of e to the iy. Now, the argument of e to the iy is simply y, but plus 2n pi, because we can always add an angle of 2n pi. So we end up with the argument equaling y plus 2n pi, and that gives us the original number z, which is x plus iy, back, plus, but we've got this extra 2n pi I appearing. So in this case, log of e to the z, it's a multi-value function. Log is always multi-valued. So we end up with this extra 2n pi I added onto the z. So, but if we have principal value log e to the z, then we're okay, because that's, you then set n equals 0 and then z equals z, and that's okay. It's fairly straightforward to show by putting z1 equals, just writing z1 and z2 in polar form, that this is still always true. Log of a product is equal to the sum of the logs, and log of a quotient is the difference of them. This is no longer the case if the ordinary log is replaced by the principal value. So now consider taking the log of z to the 1 over n. Okay, so from our definition of fractional power of z, we'll go back to 124. That's here. Okay, z to the 1 over n is given by this formula here. Okay, reproduced here. So we just take the log of this, so that's the nth root of r, so it's 1 over n times log r, and then we take log of e to the something, so the something comes down. And then we also have 2 pi ip, because what we're doing here is this is the angle without having added the extra I 2 pi n in the formula. Now I'm changing the n to a p because I've already got an n here. So sorry, this think of this n now as changed to a p. So that's where this 2 pi ip comes from. It's the 2 pi I n here, just with a p, because we're already using an n here. Okay. So now consider 1 over n times log z. So that is going to be, well, simply log z divided by n. So are these two things actually equal? Okay, so we've got log of z to the power 1 over n. We now wonder, well, could we take this 1 over n outside and just write 1 over n log z? So is this thing actually equal to this thing? It's not immediately obvious, but basically p is any integer, here q is any integer, and these two things are actually the same thing. Basically, you can just pick any value of n and any value of p in this, and you can find a value of q to get the same result here. So basically, it's any fraction of well, you got the I theta p over n to start with. Then you're just adding multiples of 1 over n times 2 pi to that, and you can add any multiple of that. So these two things are in fact the same. So we can write down that this is true. However, this expression here is not true. So strangely enough, if you got log of z to the 1 over n, where n is an integer, then you can actually take the 1 over n outside and you can write this down. That's fine. Both those things are the same. But perhaps more surprisingly, if you got log of z to the n, then that's not equal to n times log to the z, meaning that all the possible values of this are not the same as all the possible values of this. Okay. Again, I should stress this is always true. This is true if, I mean, this is okay if you're talking about the principal value of log and you're talking about real numbers, then you're fine, because then there's only one answer. But if you're talking about multi-value functions, you're allowing log to have lots of values, then you can't write these two things are not equal. And we can see this just from a simple case. Suppose z equals I and n equals 2. Just to show this is not true, we just provide an example when it's not true, and we know it's not true in general. N equals 2, z equals I, so we've got log of I squared, log of minus 1. So log of minus 1, the modulus is 1, so log of r is 0. And we just get the argument times I, which is, it's e to the I pi I plus multiples of 2 pi. So we just get that. But if we've got 2 times log I, then we work out the log I. So this log I, again, is modulus 1. It's pointing in the theta equals pi by 2 direction. So that's where this bit comes from. And then we're adding multiples of 2 pi again. Simplifying this, we end up with 4p plus 1 times pi I. And you can see this is not the same as this. You put values of all possible values of integers p in here, and you'll get, well, starting at p equals 0, well, obviously you can see these are not going to give you the same set of multiples of pi I. So they're not the same. Anyway, now you can try doing question 6. Notice this is capital Ln. You only want one value here. This is small n, and you need to show all possible values in this case.